this one. So if you consider each oscillator having some kind of wave, right? So they all have something related to this omega. So later we are talking about omega, how it is correlated with the K wave, right? So that's the wave. That means they all have the same wavelength, right? So if you excite this one actually, so you are exciting all the oscillators, right? Then what you are getting is a kind of superposition of this, all the waves. But we found that picture didn't really work to explain the low temperature heat capacity, right? So that's why we are going to introduce today Debye model. In the Debye model, what they did was, instead of using that same frequencies, we are having simple oscillators. They have different frequencies, right? Each one of them. That means each one will have wavelength different from each other, right? So you can see in one case you have longer wavelength, other case you have shorter wavelength. So eventually what you have is a superposition of all these waves, right? So that's why we have to think about something called the group velocity. Everybody familiar with the group velocity versus phase velocity? So that's why we said we need to introduce oscillators with different frequencies. Then we are going to use that same Einstein model. Only thing we have to do is, we got some value for the Einstein relationship for the CV, right? So now we are going to integrate this one over different omega. So no longer this is same, right? But we are going to introduce some cutoff for this one, say omega max. The only thing is, you need to know how many these oscillators are there for a given frequency range, right? So that means we have to introduce something called this number. This one is called the density of states. So density of states means how many these oscillators are there for a given. So that means number of these oscillators is basically this n omega times d omega. So that means n omega means really this dn over d omega. So if you know that one, you have to, so because this is for one, right, for omega, then we need to know how many of them there are, then you have to integrate all of. That's all you have to do. Once you know this one, that we know, right? Remember we introduce this number, we derive this number, so then only thing you need to know is this n omega. So today we'll talk about how to calculate this density of state. So this is really important even in the future when you talk about, here we are talking about phonons, right? So next what we are going to do is electrons. In each atom we have electrons, then we need to know electrons also have something called this density of state. So we need to work on this one. Yeah, before that let me talk to everybody about the homeworks. Not everybody has submitted all the homeworks, so I want everybody to have your homeworks submitted by maybe next Thursday. So I'm not going to give one homework today, so until you guys submit all the homeworks, because since I'm not giving exams, right, so only way I can give you a grade is based on the homework. So please work on your homeworks and have them submitted by Thursday. Then after that I will give you new homework. So far I have given 1, 2, 3, 4 homeworks, right? So this is the one due actually today, but I don't want, so all these 4 make sure you will submit by next Thursday. So I hope that will, because if you don't do that one, then you will keep accumulating in the future, right? So then you will never get to do that one. This is a good time to get and do it. Because like I said, I am not going to take off too many points if you make mistakes. I just want you to do the thing. That's the only way to learn these things. Okay, so you understand what we are getting at, right? So now let's see how we are going to calculate this n omega. Please listen to this one. This is very important because this will be used in the future when you talk about the electrons for the other properties. This density of state, this is really important. Density of states. This is a really important concept to understand. So one thing you need to understand is it's very difficult to calculate the density of states as function of your energy. Omega, remember omega is energy, right? Because E is given as h cross omega. So it's hard to calculate directly density of states as a function of energy. So what we are going to do is we are going to calculate this one in something called the K space. We already talked about K space, right? Reciprocal space. That's something similar to that one. So then once we do that, so this, I said number of states, right? Dn is given as this n omega times d omega. If you do in the K space, so that is also nk times whatever your, this I say dnk. This is space, what is the dimension of your space? It can be 3-dimensional or 2-dimensional or 1-dimensional. N can be 1, 2 or 3, right? So, typically we are talking about 3-dimensional case. But nowadays 2-dimensional materials are there, right? So we have to know how to do it for this one. So that means what you are going to do is you calculate nk. If you know nk, you can calculate n omega if you know the relationship between omega and k. So omega and k relationship, omega as a function of k, this is called the dispersion relationship. So how omega changes with k is called the dispersion relationship. So once you know omega and k, you can calculate the omega or dk, right? That's what you are. So then from there you can calculate n omega. That's the approach we are trying to do. So first we need to have that k space, right? So how do we do that? So yeah, so this is what we are going to do, right? So okay. So before that, I want to introduce one simple, most simplest dispersion relationship. Probably you all know this one. So it's mostly, if you consider, now I have this my solid, right? So crystal. So if you consider for a very simple approximation, I can consider this one as elastic medium. So just imagine this is like some kind of elastic, like you have some plastic or something, right? So then this is the simplest assumption. We consider your crystal as a elastic medium. If you consider elastic medium, you don't have atoms there, right? So later we are going to go and introduce atoms. Right now we consider this one as simple elastic medium. So then we can consider in elastic medium, if you take simple one-dimensional situation, everybody remember how the velocity in this medium, we have this elastic medium, then we have elastic wave, right? So the amplitude of that wave, suppose it is u. If you consider this one as u squared, we can show this is going to be equal to this Young's modulus divided by rho times du. So u over dx squared in one-dimensional case. This something you know from undergraduate level, right? So what is this E and rho? At the Young's modulus and the density, right? You can easily prove this one, right? So you know how to do that one. If you take a rod or something, you have delta x. If you stretch this one by delta c, you know the strain, right? By some force. What is the strain? Oh, yes. Stress I can write as force divided by area, right? So what is strain? Is delta c over delta x, right? So then the ratio between these two is the Young's modulus. So then we know F you can write it as simply mass times acceleration, right? So mass is basically mass times, density times your length times the area times your length, say delta x, right? So then that's it, right? So from if you do this one, dc over dx also you can write as dc over dx delta x. So actually this becomes. So you can expand this one. So if you connect these two, you can easily get this relationship. You can see how y and, because the ratio between these two is y, right? Strain over this one is your, in this case, E. If you do that one, you get this equation. I think you should be able to derive this equation. So what is this equation? This is basically wave equation, right? So everybody should know that one. So wave equation versus diffusion equation. If they both are second order, we call this a wave equation. If this is first order, this becomes diffusion equation, right? D squared u over, typically d squared u over dx squared equals d times du over dt. This is nothing but diffusion equation, right? So this is actually z squared. So this is first order, this is second order, right? If they both are second order, that's a wave equation. So that means this is nothing but, I can write as wave equation like this. So that means your V is E over rho, right? So if you can just compare these two, so the elastic wave velocity is simply square root of E over rho. This is important expression. So if you assume your crystal to be elastic medium, that is your velocity. So then if you know the velocity, you can define your angular frequency. What is angular frequency? Omega is divided by 2 pi times frequency, right? So then frequency is given as velocity divided by your wavelength, right? So then we can write this one as 2 pi v. Also we know your wave vector k is given as 2 pi over lambda. Then I can write 2 pi over lambda as k, right? Yeah. This becomes kv. So this is the relationship I was talking about, dispersion relationship. But this is the simplest one, right? So omega depends on your k. This is actually, we call this is a dispersionless. Later we are going to see on this crystal, if I embed my atoms, so this relationship is going to be non-linear. Here if I plot omega versus k, this is simply this, your slope is v, right? So this v is called actually group velocity. Group. Because this is, we are talking about summation of this superposition of waves, right? Everybody familiar with this group velocity versus phase velocity? So if you have like several waves with different frequencies, if you add these things, so what you are going to get is some kind of this kind of envelope, right? So the envelope is actually moving with the velocity of group velocity. Then each of these things are moving with velocity of, we call it phase velocity. So here we are talking about actually this V is the group velocity. So now if I assume my material to be elastic continuum, so I define simply the group velocity given by this omega equals k times your group velocity. Sometimes we can say it is Vg. Please remember that one. V is the group velocity. Typically we call this is dispersion length, because later we are going to show this omega is something like 2c over m sine squared k omega over 2, sorry, k over 2. So you can see now this is not linear, right? Omega and k, they have more complicated. That's a dispersion relationship. But right now, your dispersion is simply this simple one. That is the for the continuum medium. Now we will use this one when we use the ideally Vg is defined as d omega over dk, if in a more complicated way. Then phase velocity usually defined as omega over k. So in this case, d omega over dk is same as this one, right? In this case, your group velocity and phase velocity are the same. So it doesn't matter. This ideally, this is the relationship. So we are just going to talk about. Okay, now let's talk about. I said now we know one thing, because what we are going to do is this. We are going to calculate n omega, right? But we don't directly calculate n omega. What are we going to do? Calculate n k. So then when we know k, we can calculate d omega over dk. But in this case it's easy, right? What is d omega over dk? Simply Vg, right? But in later it becomes more complicated. But in our case, in elastic medium approximation, omega is Vg times k. That means, suppose this is has k dependence, so d omega is, sorry, n omega is nk dk over d omega, right? So that you can easily get d omega over dk is simply Vg. So that's so simple, right? So that's the approach. So but the only thing we need to know is how to calculate this nk. How do we do that? So to do this one, so you can do it in, so this number of, please read this one. Vibrational mode is associated with some k, right? Because each atom is vibrating with this frequency omega, so omega is related to k. That means you can represent this one as a wave. That's what we call phonons, right? So now we are going to calculate how many these modes are there for a given energy range, or maybe delta k or delta omega, any of this range. How many modes are there? So that means if the modes are, say, dn, so that you can write as that's n omega times d omega, or ne times de, or nk times dk. Actually, that's depending on your dimensionality of k. So I will show how to do that. So that is the thing, right? Between omega and omega plus d omega, that means d omega range, right? E and E plus de means de range. Here, delta k range. So I will give you very general expression to calculate for any dimension. So everybody understand what I'm trying to say here? So now how do you calculate this nk? So to do this one, we need to create some space. We call this a k space. So it can be kx, ky, kc. We have to find solutions for this waves in this k space to represent each mode. So in 3 dimension, then this is if you have some homogeneous one, it's a sphere, right? In 2 dimension, it is basically circle, right? In 1 dimension, it is basically line. So these are the each mode. So what you want to find is how many modes are there between these two for a given delta k. So I have delta k. Suppose this is my delta k. How many modes are there? Right? That's all you need to calculate. First thing is to get what are these k values. So this is what we are going to do. Is very simple. What we are going to do is use some simple boundary value problem. So suppose if I have a linear chain of atoms like this. Suppose I have these atoms here. Suppose this is S atom. This is after n, you have S plus nth atom, right? So if the separation between each one is A, that's a lattice constant. So then this length is L times Na. Suppose that is your length of your crystal. So that means this is basically total length, right? N times A. So now what I'm going to do is, I'm going to bend this one into a circle so that this point and this point will be coincident. So if I do that one, so that's how you get the boundary value. If I bend this one, you can see this is the S atom, this one. Now when I bend, so this is S plus 1, this is S plus n minus 1, this is S plus nth, right? So that will coincide with S equals A. So then you can get the series of these k values. How? So if we write the solution for this wave, if I write u as, so typically they have harmonic function, right? Solution you can write as some e, I, k, x kind of solution, right? So these are the standard solution for the harmonic oscillation. Then when, or if we want, you can put omega t terms, but we only consider x dimension, right? So then you can say when x equals s, that u value is same as x equals s plus n, right? So they both have the same u. So then if you write that one, very simple. So if I write this one, that's the solution, right? If I write s and s plus n, is that clear? The u is basically I, k. Now x is what? For the s atom, x is s times a. So for the n plus 1 atom, x becomes s plus n times a, right? That's it. So if you put that one, you can say here k s a, k is there, here k s plus n, right? Omega t is there, a omega t cancel. Then what do you get here? If you do that one, you get e I k s a, omega cancel, right? K s equals e I k s a plus k n a, right? That's it. So then you can say k s a cancel, then you get e I k n a equals 1, right? Is that clear? So now you can see, how do you get 1 for exponential term? Anything that has ei integer 2 pi times n, right? So now you can see I can get k values as 2 pi over NA. NA is actually L, right? So times your N. So for each N I can represent with some N here. You can see you can have like 2 pi over L, 2 times 2 pi over L, 3 times 2 pi over L. From every direction you can get each point. The separation between each point is, so if I write this one at the position say 2 pi over L, next one is say 2 pi over L times 2, right, like that. So but the difference between 2 is basically 2 pi over L, right? N point, and what is next one? K n plus 1 point is basically 2 pi over L times n plus 1, right? What's the difference between these two? 2 pi over L. So that's how we get the boundary value condition to create the K space. So later we will do the similar thing if you do for electrons and things like that. So here this is what I am going to say. So you get 2 pi n over n is, I just wrote, L is basically n times A. So if you do this one, you create this K values, right? Each K value is a solution for this wave equation. So now we have K space. Only thing now we have to calculate is what is the, how many states are there for a given delta K. That's very simple. Is that clear for you? So K value. So if you calculate now, like I said, the difference between these two is delta K, right? Delta K is 2 pi over L. So the separation between allowed solutions in K value is simply 2 pi over A. So that means how many modes are there for a given delta K? That is 1 over K, right? 1 over delta K. So that means you can say your number of modes for unit delta K. That means, because here we are talking about one mode here, right? So that 1 over delta K, that means L over 2 pi. This is very important thing to remember. So number of modes for a given for a unit K, right, is L over 2 pi. So L is the length of the crystal. Now if you have 3 dimension, what do you get? You get L over 2 pi in all 3 directions, right? Then you have L over 2 pi times L over 2 pi times L over 2 pi. If it is a 2 dimension, it's only this much. So here, this is what I was. So this is the number of modes per delta K, right? So you can see this is, if you do this one, what you get? L times L times L means V, right? Over 8 pi Q. Okay. So now if I know my dn, we said it is, you can write either way, right? So now we know nk. What is nk? This is the really nk, that is the number of modes per unit delta K. So that means I can write this nk as, that means dn is basically V over 8 pi cube times this d cube K. If it is 2 dimension, what do you have? So then this become dn equals a over 4 pi square, right? A over 4 pi square. Then you have d squared K. Very simple, right? If it is a 1 dimensional case,
L over 2 pi.
yeah, this is L over 2 pi times your just dk. That's it, very simple. So if you do methodically, you will never make a mistake. So here, this is for the 3-dimensional case. This is dn is basically V over 8 pi cube term. This is clear, right? So this is the number of modes per that unit is a delta K here, right? Now whole idea is how do you do it for some known volume. So we'll do that one. Is that clear? Yeah, so far. So, yeah. So now what is this d cube k if you want to do for an entire sphere? So this will be, you have to be three-dimensional. This is more like you have a total sphere, right? So that means you have the area, volume means area times your dk, right? Because eventually we need to get d omega over dk. D omega over dk. So that means if it is a three-dimensional case, you have area in k space times dk. If it is a two-dimensional case, you have perimeter times dk, right? So you have to, yeah, but I'll do it in more simple way. So because this d cube k, so here d cube k means volume. Volume is a sphere multiplied by something like this. In three dimension I have k. So if it is a homogeneous one, this is really, what is that area? 4 pi k square, right? It becomes 4 pi k square times dk. If it is a two-dimensional case, what do you get? You have 2 pi k times dk, right? 2 pi k times dk. So we'll do this one, then you understand what it means. If it's a homogeneous case, this means really 4 pi k square. Okay, so here we already write this one. So if I write this way, it's fine, right? So then, since I have this dk here, right, I can take d, because eventually I need to calculate n omega. So then I had this one. This is, you can say, dk over d omega. What is dk over d omega? Anybody remember this one? That's a group velocity, right? For the elastic medium, omega is simply Vg times k. That means d omega over dk is simply Vg. That's why I introduced that elastic medium approximation. Okay, so that's it. So from here you can calculate all the relationships. Now if you know n omega, we know this one. We calculated for Einstein model for one oscillator, right? Because they all had the same frequencies. Then we had to do d omega, but integral should be only to a maximum one. That's how we introduce something called the Debye frequency or Debye temperature. So if you do that one, actually you can easily show. Okay, before that let's calculate this one. So here, so like I said, this ds thing is 4 pi k square, right? If I substitute that one, so this is what your nk is. See, we need n omega, right? N omega is here. N omega is here, this one. So this, if you have, so we already put d omega over dk, right? That's why Vg is here. So this omega, that is 4 pi k squared, if it's a homogeneous distribution. So if you do that one, n omega becomes Vg times this becomes 4. This is the relationship. Now we calculate n omega, right? You can see n omega is now, it goes like omega squared. N density of state is going something like omega squared, proportional to omega squared. So here we have Vg. How did you get Vg cube here? K is again, you can substitute as omega over Vg. Then omega squared, then Vg squared times this Vg becomes Vg cube. So yeah, this is actually for one polarization. If you have wave, so typically it can propagate in the direction where the oscillation is happening, or it can be two other transverse directions, right? So you can have one longitudinal and two transverse. So ideally you have three polarizations, right? So that's typically, if you get the final answer, you have to multiply this by 3. Because this is for one polarization. Typically we have one longitudinal and two transverse. Okay, that's all. So now if you know n omega, you know, from here, this is, I just wrote, what will you get if you had two-dimensional case? I hope you can understand this one. Two-dimensional case, this will become A, right? So then I'm talking about here. So then this becomes what? 2 pi k, right? Instead of 4 pi k square, this becomes, instead of 4 pi square, this becomes 8 pi cube become 4 pi square times Vg. Okay, this one I wrote here. I will give you a table for each dimension, then you can easily use that one. Okay, so important thing is we now know how to calculate n omega. So anytime if you want to calculate density of state as a function of energy, what do? You first go to k space and calculate nk, then use that dispersion relationship to make d omega over dk. From that you can make the final answer. Okay, so now how do you calculate the, remember when I want to calculate the this function, right? So our n omega, then we calculated omega, d omega, we are going to see 0 to omega max. This is the CV for Debye expression, right? So this number we already calculated for Einstein, right? So that is for one frequency. So now I know n omega. So then you have to integrate to omega because they will have omega. What is this omega? Max, that's all you need to know. How do you calculate max omega? Since I know n omega is what? That's the number of modes per that d omega range, right? If you integrate that one, you get all the modes. So that means what? All the modes means each mode correspond to that particle. Then what is that total integral? That means the number of particles. So that means your n is n omega d omega 0 to omega max. Now we know n omega, right? So that is this function. We knew that function. Remember, n omega was this one, right? Constant times omega square. Now you know how to integrate this one. Very simple, right? Omega, this become omega cube over 3, right? So that's why you get 6 here. Then you substitute 0 to omega max. That should be n. So then you know omega max. Omega max is 6 pi squared Vg cube n divided by V to the power 1/3. That's how you calculate the cutoff frequency here. You get. So what is n over V? That's the particle density, right? Number of particles per unit volume. You can write as either omega max as Vg times 6 pi squared simple n. Typically we write 1/3. Simple n means capital N divided by V. Okay, so that's it, right? Now you can easily write your expression for this one. So if you remember here, okay, let me get what is the expression we knew for Einstein model here. CE, if you remember, that is, you got to remember that CE was This one, right? This. That is the complete expression, right? So then everybody familiar with this? The limits, everybody fine, right? So if I use that one now, only thing I have to do is what? Here. This one, n omega is now this some constant time omega squared, right? N omega. So this one has all these functions like constant, then you have theta e over t, then you have theta e over t divided by this exponential minus 1 squared. That's it, right? So then we have d omega. So now if you substitute this one, you will see this theta e is nothing but, this important thing to remember, theta e is actually a temperature, that is h cross omega over kb, is theta e. So that is for any general, because this has a function of without temperature, right? So then theta maximum, when this is h cross omega, remember we had omega maximum, this one is defined as theta d by temperature, because we introduced a maximum, right? That's the cutoff frequency. So please remember this one. I'm going to give this problem for you to work for two-dimensional case, then you will understand. So if you do this one, you will see you get all these things because in this expression you have omega squared now extra, right? Omega squared. So then we get here you get the same thing coming from this expression. That's what we have, the same expression. If you manipulate, you get the same thing. So because this is coming from the Einstein relationship, right? That is for 1. Now we just integrate over omega squared. So the EC also there, the same E. C is here. So then this theta over E squared, right? Yeah, this one also squared. So this one has omega, right? Because theta E has omega, that you get omega squared, right? Omega squared and new omega squared coming from n omega, that becomes omega 4. See, I have omega squared coming from this one, then I had the omega squared coming from n omega, right? That makes it omega 4. You can easily get this one. Okay, so but if you want to derive this one from the from beginning, I even put together like this. So is it clear for everybody? That is n omega, right? So this is also fine for everybody. So integrate, you get n. So now if you want to calculate total energy is what? Total energy is, this is very important. If you have one oscillator, what is the average energy of that oscillator? We know it can be filled to some state h cross omega, right? N h cross omega. But what is the average energy of that oscillator? That we calculated using that Boltzmann distribution function, right? Remember E minus beta E, that is h cross omega n. So then when you divide by the total, this one you get the average value, right? So if you do that one, that average value everybody should remember, that's the average energy, h cross omega over this one. Remember this one came from that summation thing, right? Please remember, for one oscillator, average energy is average energy of oscillator. This is what average energy of an oscillator is is given by h cross omega divided by E h cross omega over kBt minus 4. Please remember this one, it's very important. So that means this is the average energy oscillator. So you have how many oscillators in that d omega range? This is the density of state, right? Then if you integrate over d omega, you get the total energy. That we did initially even for the first one. So that's it. So then you make some kind of these substitutions. If you follow that one, so that is U, right? So then CV you have to differentiate it. We did this one before. If you do that one, you get this final answer. Or you don't have to do anything, just start from that solution, from the Einstein solution, and put it in the integral, same thing. But when I give the homework problem for two-dimensional case, you have to follow this way. But what's the only difference? This will be different, right? Two-dimensional case. Then you get different value here. Other than that, everything is the same. Everybody should do this one, otherwise you will never learn. Okay, so now we calculated the heat capacity for Debye formalism, right? So now this is also pretty complicated expression. So I will look at both high energy and high temperature and low temperature. If I go to low temperature, that means please remember this theta d is the Debye temperature. This is very important thing. If you look at materials, this Debye temperature will tell you how stiff your material is. The Debye temperature measure of your stiffness. For example, if you take diamond has very large Debye temperature. If you take a soft material, that has very low, because that tells you your stiffness of your material, right? Theta, this Debye temperature, this is given by h cross omega d over kb. What is omega d? That's the Debye, that cutoff frequency. So now if I look at low temperature, first let's look at the high temperature. That means T is much greater than the Debye temperature. In this case, your C is defined as, C is basically h cross omega over kBt. So your T is much greater means your C is very small, right? Because T is in the denominator. That means you can assume your C is going to 0, then EC becomes 1 plus C, right? So then if you plug in here in that expression 9k, this one, then you get that here EC minus 1 is basically C, right? C squared. You can see EC also become very small 1. So if you do this one, do that integral, you get 3R. It's pretty good, right? That's what we expect. High temperature, your value is, remember our CB, high temperature is 3R value, right? So that's pretty close. But low temperature, now let's see how this one. If low temperature means my T is much lower than theta d, right? So then only difference is, this is the difficult integral if your limits are finite. So in that case I can make my C maximum infinite because C is very large, right? So if you replace that one, this is integral to 0 to infinity. Please, you can do this one by Mathematica or MATLAB. If you do this one, you will find this like 4,015. So you can easily get this a finite integral. Plug in this one here, 9k, this one. So if you plug in, you get 1205. So you 5, 3, 12. You get this answer. What is that? It's a CV is directly proportional to T cube. This is a very important expression. If you are studying some material, the phononic contribution for your heat capacity at low temperature goes like temperature to the power 3. This is really important thing to remember. So later we are going to talk about electronic contribution. This is just the phonon contribution. If you take diamond, low temperature diamond heat capacity goes like T to the power 3. Now if you check this one with your experimental results, see how good now. These are the experimental results. This is the new Debye theory. So that's perfect, right? Previously Einstein one was good here, but here that dropped a little faster. But Debye model, it works really good. So Debye model is more successful than the Einstein model. Here are some of the ones I said, the theta, the Debye temperature. So you can look at some of like diamond. If you take that, Debye temperature is very high. For soft material like lithium, sodium, they are much smaller. Even like lead also soft metal, right? So you can, yeah. So lithium fluoride, these are little bit stiff material. They have much higher Debye temperature. Debye temperature has a meaning, right? Yeah.
So like what happens to the material when it reaches that Debye temperature? Does it just break apart?
No, because that tells you how difficult for it to vibrate, right?
Okay.
Yeah. This is all coming from the phonons, so vibrations. Okay. Yeah, so this is also, they plotted that times T cube. So, because CV is going like T cube, right? Previously they plotted as T, right? That's why that, but if you plot like T cube, your x-axis then is perfect straight line. Okay, I think that's what I want to talk about before we go to, so little bit more. So, because previous assumption was your crystal was simply elastic medium, right? There are no atoms in the solid. Now what we are going to do is basically introduce atoms in your solid and see how these are vibrating. So first we are going to talk about this one-dimensional monatomic. That means you have same mass atom here, like they all have mass m. So next I am going to introduce like two atom bases, two different atoms. So then you have different characteristics. So just imagine this m, mass m, all these atoms with lattice constant A. So I call this one S atom, S minus 1, S plus 1, up to S plus P. So now they all are attached by springs. That's the model, right? So you can, because these are vibrating. So I can represent each atom by springs, right? So suppose the spring constant is some C. So now just concentrate on particles. So this is at equilibrium. So at some time, so each atom will vibrate to a new position. Suppose from here, this is moving by U S minus. This is S minus 1 atom. They move by S minus 1 distance. This S atom moves by US, S plus 1 moves by S plus 1, S plus P atom moves by S plus P, right? So now I am going to calculate what is the total force on this S atom due to all the effects from all the atoms. So, but later I am going to approximate only considering the two nearest neighbors. So if I consider all the atoms, can I write the total force? So let's see, so if the force constant is C, suppose Cp. So they all are the same, right? We can assume all the force constant, the spring constant to be C. So then, if I consider this S atom, what is the total force on this one? Because this atom is moving by US, but if I consider this one, this is moving by US plus 1. So then what is the total displacement? The US plus 1 minus US, right? So that means I can write the total force as force constant times for the pth atom. So I can say US plus P minus US, right? For the pth atom. But it can be say first atom from S plus 1. That is, so then from the next one I get US plus 2 minus US, right? So, but also you have other side also. P can be negative also, right? So this one, like I can write this one as total as sigma C. I assume they all have the same P eventually. What I have is US plus P minus US. So that is my total force. So this should be equal to mass of that S atom, m d squared US divided by dt squared, right? That's the Newton's second law. So this is for the S atom, but this is the effect on this S atom from all the atoms. So is this clear for everybody? So this, if it is only nearest neighbor, P is 1, plus or minus, right? You have in both sides. If it is second, it is plus or minus 2. So this is for in general situation. So actually this is not difficult to do. So how do you solve this one? If I write my solution, you can see how that one, this is how it's going to oscillate, right? Between your equilibrium position. So this is how you write the equation, right? M d squared over dt squared Cp, this one. So how do you solve this one? We have to assume solution for US, right? So it's typically we use harmonic solution. US has some exponential EIK. This is the solution. For the S atom solution is some amplitude EI kxs minus omega t. K, what is xs means? S atom, so that's distance is if you have some origin, S times A. So now just take the derivative of this one. You have to take derivative twice, right? If you take first derivative, you get minus I omega. If you take the second derivative, again minus I omega, then you get omega squared, right? So that's it. So then if you write that one, here, minus I omega squared, yeah, that one. So then here also I have to plus, what is US plus P? K, this is S, S plus, the S plus PA, right? XS means, XS means A times S, X plus, S plus P means A times S plus P, right? So we just put here that is S plus P. S is simply this one, right? You can see omega t term cancel. What you are getting is this one. Yeah. KSA also I can take out, right? KSA also comes out. They cancel each other. So then what you are getting is simply, I think everybody can follow this one, right? So that's the final answer. Minus m squared. These two cancel. This. That's easy, right? So this is the general expression, effect from all the atoms. But here you have atoms from both left and right. Now if I want to only consider to the right, what do I do? But here P is for both positive and negative, right? I can make only positive by adding P minus term into this one, right? So that means I can make, here P means all P. P can be negative or positive. I will put P only positive by putting another term that has P equals negative P, right? That means I have something like Cp EIKPA minus 1. Then if I put plus, I have E IK minus P, right? Minus P A minus 1. So you get minus 2 here, right? So if you do that one, this P becomes only positive, because now I have already included negative term into that one. So then what you get is simply this one. Remember how I got 2 right here. So if you do this one, P is only now positive. We don't have to consider negative term. Okay, so now what is this one? Ex plus E minus X means 2 times cosine, right? Everybody remember? Cosine X is basically E Ix plus E minus Ix divided by 2, right? That's what we have 2. This is plus KPA. Then, yeah, so I put 2 out. So then I have this 2, 1, 2. Okay, so that is general situation considering all the atoms. But for simple consideration, we only consider only nearest neighbors. Nearest neighbors means P is only 1, right? You don't have to consider left one. We already considered that one, right? So then your answer is minus m omega squared is simply 2Cp cosine P is simply 1, right? Cosine PA minus 1. That's it. So only the nearest neighbor, if you consider only the, yeah. So here just wrote 1 minus cos means 2 sine squared half, right? Remember this one, cosine 2x is 1 minus 2 sine squared x. Remember? So that means that cosine 1 minus cosine 2x means 2 sine squared half of this one, right? So that's why you get half here. Simple. You should remember this one. So then if I consider only the nearest neighbor, that's the answer. Omega squared is 4C1 divided by mass sine squared this one. That means omega is square root of 4C1 over m sine half Ka, right? This is only the positive value. So this is not like omega equals kVg, right? This is different dispersion. If you plot this one, actually what you are getting is something like this sine, right? But we are only plotting up to this. If you remember your brilliant zones, anybody remember that? This is still K space, right? So this is actually pi over A. This is minus pi over A. You can see here, this is actually similar to that elastic medium, right? So these are still, so actually we call these modes as acoustics modes. That means these are low frequency modes. Low frequency means, low frequency and also low K value, that means high wavelength. So So these are acoustic phonons. So that's what you have to know, like if you have some light interacting with these phonons. So anybody know the name for light interaction with this, the acoustic phonons? It's called the Brillouin scattering. Probably you all know. Later we are going to talk about high frequency modes. So they are called optical modes. So anybody knows what is interaction of light with optical modes? That you all have done, but you don't remember. That's the Raman scattering. In Raman scattering, you have these optical phonons, so they interact with the light. Here we are talking about this. If you have these monoatomic ones, they don't have optical modes. They only have acoustic modes. They have low frequencies. They interact. They call the. Later we'll talk about the Brillouin scattering. It is clear for everybody, omega. So this is how it looks like. If you, yeah, this is. You can see this is still like that elastic medium, right? So, but here, this becomes actually. If you come here, what is your that group velocity here? D omega over dk becomes 0, right? At the Brillouin sound border, your the group velocity becomes 0. Actually, this means actually that wave is getting reflected from the boundary. So we don't have to go. So this is your first Brillouin zone, right? So this is your second Brillouin zone. So we never talk about anything beyond first Brillouin zone. Everything we can explain from this one. If you won't consider this one, you can actually fold it back to the first Brillouin zone. This is called zone folding. So you don't have to worry about anything about here. That is corresponding to actually this value. This is subtracting G vector. So if you do that one, this point is same as this point. This point is same as this point. So you can always bring back. So please remember, these are the Brillouin zone. Remember, Brillouin zone means what? The Wigner size cell of the reciprocal space, right? That's all. So yeah, these are your k vectors, right? If you take this one, intersect here, then you get the Brillouin zone boundary. This 2 pi OA, right? But this is the Brillouin zone boundary. The separation between the, the width of the Brillouin zone is 2 pi OA. Pi OA minus pi OA. Okay, so if somebody wants, I just wrote down this one to do only considering nearest neighbor rather than doing that infinite number. So only if I have US, also I wrote as a negative number. Previously I wrote this one minus this one, that's why I had the positive. Here I wrote like this one minus this one, then you have opposite direction force, right? So this is US, S plus 1, S minus 1, only the nearest neighbors, just for you to understand. Again, you just plug in your solutions, you get that same here. Just to, but remember the previous one we just did all the summations, then we approximated, right? But you can start only considering only the nearest neighbor. Yes, to understand how to do that kind of thing. So like this is what I was trying to say. Anything more than this is a 2k maximum. Anything above this one is same as your that what you have in the first Brillouin zone. Just to show it. Okay, so Vg is 0 at zone boundaries, right? If you take d omega over dk, when you take the derivative, this becomes cosine, Ka cosine 90 becomes 0. Okay, so let's go to Yeah, give me a few more minutes. Actually, people have measured this frequency as a function of omega. Sorry, k. That's the wavelength, right? So everyone remember that our symmetry points from gamma is your center. So then you have x points to one of these surfaces. So this is some FCC. That is right. So if you look at this are k, right? Along this one you can change your k vector. So if you go from here to here, this is a brilliant zone boundary, right? Because this is actually coming to the reciprocal scale. This is x point is your brilliant zone. You can say this is becoming perpendicular to that one. But if you look at this aluminum 1 0 0 direction, remember we talk about directions, right? 1 0 0 means in this case this 2 0 directions, they are pretty much same, right? They are degenerate. So that means you will only see one longitudinal and one transverse wave. So you will see one longitudinal one transverse one. But if you go to 1 1 0 direction, that means they are two different directions. In that case you will see one longitudinal and two transverse ones. Because in 3 dimension you should expect to have 3 modes, right? But also it depends on what direction. So again, this is your zone boundary here. So yeah, I will stop here. Yeah, then next one I will talk about what happens if you have in this chain, you have two different atoms, M1 and M2. Previously, they all were same, right? In this case, you have something called the optical modes also coming. Then you need to understand longitudinal, then acoustic, optical, transverse, longitudinal. I will explain all these things. Okay, I'll stop here. So please take your time and finish your homeworks by next Thursday. All the homeworks.